Hey everyone, and welcome back to the Explainer. I am so thrilled you're tuning in today. In this Explainer, we are going to track the invisible, absolutely thrilling journey of moving particles to unlock the secrets of electricity and chemistry. If you've ever stopped to wonder how the physical materials around us actually interact at a microscopic level to power our entire world, well, you are in the exact right place. We're going to break down some incredibly fascinating concepts, and I promise you, by the time we wrap up, you'll be looking at a simple battery or even just a glass of water in a completely new way. But before we really get into the weeds, I want to toss a core question your way. We all know electricity flows through the metal wires plugged into our walls, right? But how on earth can electricity flow through a liquid when there are absolutely zero wires present? How does the current actually cross that watery gap? It completely challenges our everyday assumptions, doesn't it? To figure this out, we've got to zoom way in and look at what's happening down at the microscopic level. Okay, let's dive into our roadmap for today. We're starting with conductors and insulators, then moving into the magic of electrolytes, uncovering the rules of oxidation and reduction, taking a peek inside the electrolytic cell, and finally, we'll bring it all together with electrolysis in action. Section 1. Conductors and insulators. Let's talk about solid materials. So the defining factor that separates a conductor from an insulator is basically a bridge. And that bridge is made entirely of free electrons. Metals like copper and silver, they are packed with these free electrons, allowing an electrical current to just slide right on through. Insulators, on the flip side, think diamond or wood, have locked-in electrons. No free electrons means absolutely no electrical flow. But hey, notice a surprise guest in the conductors column? Graphite. Even though it's a nonmetal made of carbon, the way its atoms bond actually leaves one electron free per atom, so it acts like a conductor. Keep graphite in the back of your mind because it's going to be a real hero in our story a little later on.
Section 2, the magic of electrolytes. We are entering the fluid world.
Now this right here, this is a massive aha moment. This is where all the rules change. In solid conduction, like we just talked about, the flow is purely free electrons zipping through a wire, and crucially, the wire itself doesn't chemically change at all. It's just a highway. But liquid conduction? Whole different beast. Electricity flowing through liquids doesn't rely on electrons. It relies on moving ions, charged particles. And here is the kicker. When electricity flows through these liquid ions, it actually forces the liquid to chemically break apart. It's a process called decomposition. The actual passage of electricity changes the very chemical nature of the substance. But look, just because a liquid is, well, a liquid, doesn't automatically mean it conducts electricity. Let's bust a very common myth right now. Pure water, meaning water with absolutely no dissolved minerals in it, does not conduct electricity. Why? Because it lacks those crucial free ions. We call liquids like this non-electrolytes. Other everyday examples would be ethanol, petroleum oils, and sugar solutions. Because their molecules don't break apart into charged ions, the electrical current just hits a total dead end. Section 3. Oxidation and reduction. Let's learn the chemical rules. Historically, scientists first observed these reactions through the lens of oxygen. The old concept was pretty straightforward. If a substance gained oxygen, it was oxidized. If it lost oxygen, it was reduced. So like taking black copper oxide, reacting it with hydrogen, and watching it reduce back into pure copper. But, science evolves. Chemists eventually realized these reactions were happening even when oxygen was literally nowhere to be found. So they expanded the definition to the modern concept, realizing that what was truly being transferred weren't just oxygen atoms, but the electrons themselves. Okay, let's really nail down this modern terminology. I'll admit, it can feel a bit backward at first, so stay with me. Oxidation is the process of losing electrons. Because electrons have a negative charge, losing them makes the atom's overall charge more positive. Reduction, on the other hand, is gaining electrons. You are literally reducing your positive charge by adding negative electrons to satisfy a deficit. Just remember, these two processes are totally tied together. If one substance loses an electron, another substance has to be right there to catch it. Which perfectly tees up our next, admittedly tricky concept, the agents. It's a completely counterintuitive naming convention, but let's break it down simply. The oxidizing agent is the chemical that causes the oxidation of something else. To pull that off, it steals their electrons, which means the oxidizing agent itself gets reduced. And conversely, the reducing agent gives away its electrons to help something else reduce, meaning the reducing agent itself gets oxidized. The golden rule here, Always look at the starting reactants on the left side of your chemical equation to identify your agents, never the final products. Just to give you a few concrete, recognizable examples, here's a quick list of the heavy hitters. These are your strong oxidizing agents: oxygen, hydrogen peroxide, potassium permanganate, and potassium dichromate. These materials are incredibly greedy for electrons. When you drop them into a reaction, they forcefully rip electrons away from other substances, getting themselves reduced in the process.
Section 4. Inside the electrolytic cell. Time to check out the physical setup.
So to actually force these chemical changes to happen using electricity, we need a very specific physical setup. First up, we need a direct current battery. This is our engine, pumping electrons in one direction. Second, we need electrodes to dip into our liquid. Remember our surprise conductor from earlier? Graphite is heavily preferred here. We use inert materials like graphite or platinum because they easily conduct the current but won't accidentally react with the chemicals we're trying to separate. And third, we need the electrolyte itself, either a melted salt or an aqueous solution that's just packed with free-moving ions. The absolutely crucial point here is understanding the two different electrodes in our cell. Connected to the negative side of the battery is the cathode. Because it's swarming with negative electrons from the battery, it acts like a magnet for positive ions, which we call cations. At the cathode, those positive ions grab electrons. They get reduced. Over on the other side, connected to the positive terminal, is the anode. It attracts the negative ions, or anions. These negative ions dump their extra electrons right into the anode, meaning they are oxidized. Those electrons then ascend out of the anode and travel back to the battery, completing the whole electrical circuit. Section 5. Electrolysis in action. Let's get to splitting compounds. We've built the foundation, we know the rules, now let's see exactly how we apply this knowledge to split actual materials. Let's deconstruct this methodically using lead bromide as our guinea pig. Step 1 is absolutely vital. We have to melt the solid lead bromide crystals using a continuous flame. If it stays solid, the ions are locked in a rigid grid and can't go anywhere. Melting it frees those ions so they can actually move. Once we have a liquid melt, step 2 begins. We flip on the battery. Immediately, the charged ions start migrating to opposite poles based on their charges. And step 3, the magic happens at the electrodes. Let's zoom in on those half reactions. Take a look at what goes down at the negative cathode. Our positive lead ions, the Pb2+, pull up looking for electrons. Because they have a positive 2 charge, they need exactly 2 electrons to balance out. The cathode eagerly provides them. They gain those 2 electrons, which means they undergo reduction, and literally transform from invisible, dissolved ions into pure, solid, shiny lead metal right there at the bottom of the electrode. At the exact same time, over at the positive anode, the negative bromide ions are arriving. They're carrying extra electrons that they desperately want to get rid of. 2 bromide ions will each drop off an electron at the anode, and since they are losing electrons, that means they are undergoing oxidation. When they do this, they pair up to form Br2, which is bromine gas. If you were standing in a lab watching this, you'd see an incredibly exciting visual. Distinct brown bubbles of gas vigorously forming at the positive electrode as the electrons are stripped away. We literally just use electricity to tear a molecule in half. To really solidify this for you, let's run it back and apply the exact same logic to a second example: aluminum oxide. Once you master the steps, you can unlock any chemical equation. First, we melt the aluminum oxide. The positive aluminum ions migrate over to the cathode, where they each gain 3 electrons. Reduction happens, and pure liquid aluminum metal is produced. Meanwhile, the negative oxide ions rush to the anode, dump their extra electrons, oxidation happens, and they bond together to form a colorless gas bubbling up, pure oxygen. The rules apply perfectly, every single time. So we've seen what happens when we use extreme heat to melt these salts into pure liquids. But let me leave you with a bit of a provocative thought to set up the next level of your chemistry journey. What happens if we take the easy route? What if, instead of melting these salts, we simply dissolve them in water to make an aqueous solution? Do the water molecules just sit back and watch, or do they jump right into the electron race at the electrodes? Think about that. Thank you so much for exploring the invisible world of electrochemistry with me today. Stay curious, keep learning, and I'll catch you in the next explainer.